Lesson 6.4 is about inequalities for one triangle. Okay, so the first theorem has to do with the angles of a triangle. So if we're looking at one triangle and we want to know how do its angles compare in size, we can examine the sides of the triangle. Now in these examples, we're just going to be comparing two sides and two angles. Okay, so when I say big and small, I mean big and small with respect to each other. A bigger angle, a smaller angle, a bigger side, a smaller side. So in the drawing here, I have a longer side, big as the longer side of this triangle, as compared to the other side that I've labeled small. So just comparing those two sides, big as the longer side, small as the shorter side, well, it shouldn't be any surprise that the angle that's opposite the bigger side is going to be a bigger angle than the angle that's opposite the smaller side, because I don't open as wide. So the angle opposite the smaller side is smaller than the angle opposite the bigger side. So the inequality is that an angle opposite a longer side of a triangle is longer than the angle that's opposite the shorter side. And I think that makes rational sense. Okay, and the next theorem is just the same thing in reverse. When we examine the sides of a triangle within one triangle, if I compare two angles to each other, and one is smaller and one is bigger, then I think it follows logically that a smaller open angle is going to have a shorter side across from it. So with respect to these angles, the sides opposite the angles have the same relationship. So we can state that theorem as that the side opposite the bigger angle is going to be greater in length than the side opposite the smaller angle. Okay, the next theorem actually has a name. It's called the triangle inequality theorem. And what this says is that if you take three sides of a triangle and you choose any two of them, that the sum of those two sides has to be greater than the length of the third side. Has to be greater than the length of the third side. So let's go through a little example of how this works and why it's true. Okay, so let's take this triangle ABC and add some side lengths. And this is not drawn to scale at all, so you have to imagine this, these side lengths very flexible. Let's say that AB is 3, AB is 7, and the length of AC is 3. Okay, what does that say about the length of BC? Well, what could BC be? It can't be smaller than 4. And the reason it can't be smaller than 4, 7 minus 3 equals 4, is that if I made it exactly 4, then side CA and side CB couldn't be set apart at an angle and still reach 7 across on the bottom. So it has to be greater than 4. And what else does it have to be? It has to be less than 10, less than the sum of 7 plus 3. Okay? It has to be less than 10, because if it was more than 10, when I added up the side that was 7 and 3, they couldn't be stretched in an angle to meet the endpoints of a segment more than 10 long. So in short, if you know two sides of a triangle and you want to know what can the third side be, it has to be bigger than the difference between the two other sides, and it has to be less than the sum of the two other known sides. So as an example, let's choose a side length. Let's say 5 is greater than 4 but less than 10. Let's say that side is 5. Now what happens is any two that you add up, if you add up these two, 10, they're greater than 5. If you add up these two, they add to 8, they're greater than 7. And if you add up the 7 and the 5, that's 12, that's greater than the other side of 3. So any two sides I pick has a sum that's greater than the length of the other side, the third side. Okay, so let's show a few examples of these theorems. In this first example here, I have a triangle with two angles shown, and I'm supposed to find the longest side and the shortest side of this triangle. So let's make this triangle RST like so. Okay, so I see I have two angles that I know already, 105 and 46. So if I add those up, I get a combined measure of 151. And if I take that away from 180, I know now that I need to find the measure of that third angle. That third angle is 29 degrees. So I'll fill that in up here. Okay, now just comparing the three angles, I can find the longest and the shortest side of this triangle, and then the other one would be the middle length side. So opposite the largest angle of 105 degrees will be the longest side. So that is side RT. And then the smallest angle is the 29-degree angle. So opposite the smallest angle will be the smallest side, which is side RS. So that just shows how to apply that theorem to any triangle. Okay, then in this exercise I have a triangle, and the lengths of two sides of the triangle are 8 and 13. Now, what can the length of the third side be? The length of the third side has to be greater than some number and less than some other. It has to be inside of a range, so that I make sure that when I pick any two sides, their lengths have a sum greater than the third side. So the way we do this is I take the difference between the two known sides. So 13 minus 8, I subtract the bigger one minus the smaller one. And so I know that this is a 5. The third side has to be more than 5. It can't be exactly 5. It has to be greater than 5. And it has to be less than the sum of those two measures. So that would be 13 plus 8, or 21. So the third side has to be greater than 5 and less than 21. Okay, this last example is a good one. I've got two triangles, one kind of with its hypotenuse, two right triangles. The hypotenuse of one is one of the legs of the other. And I'm supposed to compare the angle measures of angle 1, 2, and 3, which are labeled. So I have to force rank them, put them in order from biggest to smallest. So let's first of all start with the angle that's on the ground, with the right angle up at the top. And I see that I have one side of the angle of one side of the triangle that's 98 and one that's 97, with a 90-degree angle between them. So I know this is almost an isosceles triangle, but not quite. And I can tell from this that the angle that is opposite the 98 side is bigger than the angle opposite the side that's 97, because it's opposite, the bigger side. Okay, bigger side, so that's a bigger angle. And in fact, I know it's greater than 5 degrees, and I'm going to save that for later use, because I know if that was an isosceles triangle and both of those side lengths, the 98 and the 97, were both the same length, those two angles would be 45-degree angles. So I know this one's got to be a little bit more than 45 degrees. And I know that angle 2 now has to be a little bit less than 45 degrees. Okay, and I know that that's smaller now than angle 3. So for starters, I can say, okay, angle 3 for sure is bigger than angle 2. So now let's compare angle 3 or angle 2 to angle 1. So I notice that in addition to being a right angle, that the angle with angle 1 in it up here at the top is isosceles. And so I automatically know now that the base angles here of this isosceles are both exactly 45 degrees. Okay, so those are both exactly 45 degrees. So now I can compare angle 2 and angle 1. I see they share this common side that's 98, and opening up off of that, angle 1 is a bigger angle than angle 2. So, because it's 45 degrees, and angle 2 has to be less than 45 degrees. So I know now that angle 1 is greater than the measure of angle 2. I also now know that the measure of angle 3, which we know is bigger than a 45-degree angle, is greater than the measure of angle 1. So if I put these all in order from top to bottom, angle 3 is greater than angle 2, but angle 1 is greater than angle 2, and angle 1 isn't as big as angle 3. So from biggest to smallest, it would go angle 3, angle 1, angle 2. So I can conclude by saying measure of angle 3 is greater than the measure of angle 1, which is greater than the measure of angle 2. And that's it.